Welcome all. In this lecture, we are going to study about solution of wave equation in rectangular waveguide. So here is the rectangular waveguide, which is having horizontally oriented x-axis and the vertically oriented y-axis. Let us assume that in this waveguide, the wave is propagating in positive z direction. So this z-axis is being perpendicular to both the y-axis as well as x-axis. Now, this rectangular waveguide also have some cross-section area. So the breadth of this rectangular waveguide is represented by A and the width of this rectangular waveguide is represented by B only. And let us assume that the length of the rectangular waveguide is nothing but L only. So here is the length of rectangular waveguide. If we talk about the electric and magnetic wave equation in the frequency domain for this rectangular waveguide, then it will be represented like this, where for the electric wave equation it will be given as del 2 E equals to gamma square into E, and for the magnetic field equation it is given as del square H equals to gamma square H. Let us give it as equation number 1 and it is as equation number 2. Here, if we talk about the value of gamma, then we know that gamma is nothing but propagation constant, and the value for the gamma will be equals to j omega mu sigma plus j omega epsilon. And the gamma, that is propagation constant, can also be represented like alpha plus j beta. Here alpha denotes the attenuation constant and beta denotes phase constant. So this is all about the propagation constant associated with rectangular waveguide. Now for this rectangular waveguide, the rectangular components of electric field and the magnetic field should satisfy the Helmholtz equation. So we can write it as the rectangular coordinates or components of electric and magnetic field should satisfy Helmholtz equation. Where this Helmholtz equation in the rectangular component of electric and magnetic field can be given as del square psi, that is being equals to gamma square psi. Here this del square can also be written as del 2 over del x square plus del 2 over del y square plus del 2 over del z square. This is the representation for del square in terms of the rectangular component. Now if we substitute the value of this del square in this equation, then we get the modified equation as del 2 over del x square into psi plus del 2 over del y square of psi plus del 2 over del z square of psi, that is being equals to gamma square psi. So gamma square psi. This is our equation number 3rd. If we analyze this equation, then we can say that it is a linear and inhomogeneous partial differential equation. So we can solve this equation by the help of method of variable separation. So by method of variable separation, we can say that the value of psi, that is being equals to x, y and z only. This is our equation number 4. If we talk about this capital X, then we can say that this capital X is a function of small x, that is here small x coordinate only. If we talk about this capital Y, then this capital Y is also a function of small y coordinate only. And similarly, this capital Z here is the function of this small z only. Here is small z only. So this is all about this x, y and z that we written here. So here is the equation number 3 and here is equation number 4 that we evaluated. Now if we substitute the value of psi from the equation number 4 in the equation number 3, then we get the expression as, on substituting value of psi from equation 4 in equation 3, then we get del 2 over del x square of capital X, Y and Z plus del 2 over del y square of capital X, Y and Z plus del 2 over del z square x, y and z, that is being equals to gamma square into psi. So this is the equation that we get. And if we take the derivative of x, y and z with respect to small x, small y and small z, then the partial different derivative will then convert it into the normal derivative and we get yz d2 over dx square of capital X plus xz d2 over dy square of capital Y plus xy d2 over d small z of capital Z, that is being equals to gamma 2 into psi. Now let us divide this equation by equation number 4. So here is the equation number 5. Now dividing equation 5 by equation 4. So on dividing this equation by this equation, then let us divide the first term with x, y, z. So on dividing we get 1 over x d2 capital X over dx square plus 1 over y d2 capital Y over dy square plus 1 over z d2 capital Z over d small z square, that is also being equals to gamma square, because this xyz is nothing but sign and psi will get divided by this sign, so we will get the remaining term as gamma square only. Let us give it as equation number 6. Now we can say that all the terms in the left hand side are constant only and each term can separately be equals to constant term. So if we write this expression in the form of constant, then we can write it as minus of k x square minus of ky square minus of k subscript z square, that is being equals to gamma square. This is equation number 7. These three constants we assumed for this corresponding values. Now if we compare equation number 6 and equation number 7, then we get the value of these three constants separately. So on comparing equation number 6 and equation number 7, we get the value of minus kx square, that is being equals to this first term. So 1 over x d2 capital X over d small x square, and if we simplify it, then we will get the value of the derivative, that is d2 capital X over dx square, that is being equals to minus of kx square into capital X. This x will get in the LHS, then we get this expression. Similarly, for the second term also, the value of minus ky square will be this second term, that is 1 over I y d2y by dy square. So minus ky square equals to 1 over capital Y d2 capital Y over dy square. On simplifying, we get the value of derivative, that is d2 capital Y over dy square is equals to minus of ky square into capital Y. Similarly, for the third equation, we get the value of minus kz square, that is being equals to 1 over z d2 capital Z over dz square, and we get the value of d2 capital Z over dz square equals to minus of kz square into z. These are the three values of the constant in the terms of derivative. Now the general solution for each differential equation will be given as the general solution is given as, for the value of capital X, we will get the general solution as a sine of k into small x plus b cos of kx to small x. This is our equation number 8. Similarly, for the value of capital Y, we get the general solution as c sine k subscript y into small y plus d cos ky. This is our equation number 9. And for the value of z, we get the solution as e sine k subscript z into small z plus f cos kz to small z. This is our equation number 10. Now we finally get the value of x, y and z. If we substitute the value of x, y and z in this equation number 4, then we get the value of psi in the terms of general solution. So let's substitute it. So substituting the value of x, y and z in equation number 4, we get the expression as psi, that is being equals to, in place of x we will write this whole expression, that is a sine k subscript x into small x plus b cos k subscript x into small x in multiplication with the value of y, that is replaced with this value. So c sine k subscript y into small y plus d cos ky into small y in multiplication with the value of z, that is here. So here is z value, that is e sine kz plus f cos kz. So this is the general solution for the value of psi. Now let us have a look at some parameters that are associated with wave equation. So the first parameter associated with wave equation is nothing but propagation constant. Since we know that the propagation constant is denoted by gamma only, and the expression for gamma is equals to alpha plus j beta. Here alpha is the attenuation constant and beta is the phase constant. And if we talk about the lossless dielectric, then we can say that for lossless dielectric, the value of propagation constant, that is gamma, that is being equals to j omega under the root mu epsilon. This is the value of propagation constant for lossless dielectric. And if we solve the value of gamma square, then it is equals to minus of omega square into mu epsilon. This is all about the value of propagation constant for lossless dielectric. Now let us discuss the second parameter, that is cutoff wave number. The cutoff wave number is always be represented by the symbol, that is Kc. Here if we talk about the representation for cutoff wave number, then it will be always equals to under the root kx square plus under the root plus ky square. And the value of kx and ky we discussed earlier. Now let us discuss the third parameter, that is propagation constant. For the wave in waveguide. See, this is the propagation constant for the wave which is traveling in the waveguide, and this is completely different propagation constant from this propagation constant. And the propagation constant for waveguide is represented by gamma subscript g. This differs the symbol from this symbol. Now if we talk about the value of gamma g, first of all we will talk about gamma square g. So it will be equals to gamma square plus kc square, where gamma is the propagation constant and kc is the cutoff wave number. And the value of gamma g, that is propagation constant for guide wave, is equals to plus minus j under the root omega square mu epsilon minus of kc square. This value we get after replacing the value of gamma square by this value. So this is all about the three parameters that are associated with wave equation. Now let us have a look at the three cases that are associated with wave propagation in waveguide. So here is case number 1. According to the case number 1, if the value of omega square mu epsilon is equals to the value of cutoff wave number having square. In this condition we can say that there will be no wave propagation. So there will be no wave propagation. But why we have written that there is no wave propagation? The reason is, since we discussed the propagation constant for the guide wave that is represented as gamma g, that is equals to plus minus of j under the root omega square mu epsilon minus of kc square. And according to this fact, if the value of omega square mu epsilon is equals to kc square, then on substituting it in this expression, the value of gamma g will be equals to 0 only. And since the value of propagation constant is 0, that's why we say that there will be no wave propagation. And since there is no wave propagation, that's why the cutoff frequency is given as fc, that is being equals to 1 over 2 pi under the root mu epsilon under the root kx square plus ky square. So this is all about case 1. Now let us have a look at the case 2. According to the case 2, if the value of omega square mu epsilon is greater than the value of kc square, if this happens, then we can say that the wave will propagate in the waveguide. So the wave will propagate. Since the wave is propagating inside the waveguide, then we can get the value of gamma g, that is being equals to plus minus of j beta g. And if we replace this beta g with its value, then the value of beta g is equals to omega under the root mu epsilon under the root 1 minus fc over f whole square. This is the value of the propagation constant for the waveguide. Let us discuss the last case, that is case number 3. According to the case number 3, if the value of this omega square mu epsilon, that is being less than kc square, if this happens, then the value of gamma g, that will be equals to the attenuation constant, that is alpha g, and the value for the alpha g is nothing but equals to omega under the root mu epsilon under the root fc over f whole square minus 1. This is the value of attenuation constant. And since the value of omega square mu epsilon is less than kc square, then in this case the value of the wave will be attenuated. So the wave will get attenuated. This means that if the operating frequency is below the cutoff frequency, then the wave will decay exponentially and there will be no wave propagation. Therefore, the solution to the Helmholtz equation is given as sine, that is being equals to a sine kx small x plus b cos kx small x in multiplication with C sine ky into capital small y plus D cos ky small y in multiplication with e to the power minus j beta gz. This is our final solution to the Helmholtz equation that we discussed. So this is all about the solution of wave equation for rectangular waveguide. If you like my videos, then do subscribe my channel and please hit the like button. Thank you.